So, good morning everyone. So, in last class we have discussed the power gain and effect and directive gain. Okay. Today I am going to discuss about effective area. Okay. So, what does it mean effective? What does it effective area mean? Effective aperture is the ability of an antenna to extract energy from the electromagnetic wave, called as effective area. Okay. So, the effective area is defined as the ability of an antenna to extract energy from the electromagnetic wave. So, effective area is defined as the means electromagnetic wave నుంచి ఎనర్జీని ఎక్స్ట్రాక్ట్ చేసే ఎబిలిటీ ఒక యాంటీనాకు ఉండే ఎబిలిటీని దాన్ని ఎఫెక్టివ్ ఏరియా అంటాం. సో ఎఫెక్టివ్ ఏరియా is defined as the power ratio of the power received in the load. So it is like a means one current source is connected to the one resistance and connected to the one load resistance. Here the one resistance which is equal Z is equal to resistance radiated plus J into X. So load resistance is defined as the R radiated minus Jx. Okay. So effective A is defined as the ratio of area is defined as the ratio of power received in the load to the average power density produced at that point. Means effective area is defined as the, so I repeat again, average means ratio of the power received in the load to the average power density produced at that point. So the voltage induced in the antenna, which is voltage, you know that the distance times the electric field. So electric field times dl. So where modulus of electric field is the magnitude of the electric field intensity produced at the receiving point, and dl is the length of the Hertzian dipole. The current flowing in the load is defined as the voltage VCO divided by the sum of the resistance. So because these two resistance are in the series configuration, so these two resistance should be summed up. So substitute the values of Z is equal to R radiated plus Jx means power resistance load impedance of load impedance, which is equal to R radiation minus Jx. Here Jx will cancel out, Jx plus Jx minus Jx will cancel out. So I is equal to VCO divided by 2 radiation means resistance radiation. Okay. Then power delivered to the power delivered to the load is, we already know power is equal to I square R. So here current is represented in terms of root mean square. So power is equal to power radiated, which is equal to I square I RMS square R radiated. I is equal to, so here I is equal to I VCO divided by 2 means resistance radiation. So which is, so if you substitute here, you will get VCO divided by 4. So here 8 is there, the 8 is, so there is a small mistake here. This is not 8, this is a 4. So make it correction. So VCO square divided by 4 R radiated. So now VCO is the product of magnitude of electric field intensity into the length of the Hermitian dipole dl. Substitute in in this expression, so you will get PR is equal to E square dl by 4 pi 4, so not pi, 4 into R radiated. Okay. So maximum aperture is given by the, I already said the maximum area means effective area is defined as the power radiated in the load, the ratio of the power received in the load to the average power density produced at that load. So maximum power received divided by the maximum means average power density. PR max divided by P average. PR max is the E square dl square divided by 4 radiation means R radiation divided by P average 1 by 2 E square by neta naught. So if you simplify this, you will end up with dl square neta naught by 4. So there is, you will get a 2 here, 2 into R radiated. Okay. So neta naught is equal to 120 pi. You know that the R radiated is also we have derived in the subunit 1 R radiated which is equal to 8 pi square dl by lambda whole square. Substitute these values, you will get the maximum effective aperture. Okay. So let us discuss the antenna beam width and antenna or bandwidth. So antenna beam width is the this is the off 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 pole beam width. Okay. This is the distance between the this major loop. The distance of this radiation is the antenna beam. So antenna beam width or off power beam width. So I have already drawn this this radiation pattern in offline class. So this HP double BW is the off power beam width, means off of this major loop, distance of this radiation of that antenna beam width or off power beam width. It is a measure of directive of the antenna. It is a measure of directive of the antenna. Directivity of antenna. It is an angular width in degrees. It is a measured on the radiation pattern on a major loop. I already said to you, it is measured only the measured only on the radiation pattern on the major loop. Antenna beam width is defined as the angular width. Antenna beam width is defined as the angular width in decrease between the 2 points on the major loop of a radiation pattern where the radiation pattern decreases to the half of its maximum. సో యాంటీనా బీమ్ విత్ అంటే ఏంటంటే ఇప్పుడు మీ రేడియేషన్ ప్యాటర్న్లో మేజర్ లూప్ ఉంది కదా, దాంట్లో హాఫ్ ఆఫ్ ది మేజర్ లూప్ రేడియేషన్ ప్యాటర్న్ యొక్క మేజర్ లూప్ ఉంటుందో ఆ డిస్టెన్స్ని what we call it as antenna beam width. Antenna beam width is defined as angular width in decrease between the 2 points on the major loop of a radiation pattern where radiation power decreases as the half of the maximum power radiated. Okay, so this is the antenna power pattern in polar coordinates. I already discussed to you. This is the here written the main loop. Main loop means major loop, minor loops. Okay, the antenna power pattern in the rectangular coordinates on logarithmic scale. Okay, the beam width is also called as half power beam width. It is clear that the power is maximum at the point P. So the here at P1 and P2 is the distance, that's the beam width. Okay, so at that point the power is maximum, while it is off at the points P1 and P2 hence rectangular width between P1 and P2 is an angular antenna beam width or half power beam width. The beam width is also called as a 3 dB, means decibel I think so, beam width as a reduction of power to the half of its maximum value corresponding to the reduction of the power. The radiation pattern is described in terms of angular width between first null or first side loop. Such angular beam width is called a beam width between the first nulls. But radiation pattern another is described in terms of angular width between the two nulls or first sides loops. The directivity is related to the solid angle or beam area. Directivity is equal to 4 pi divided by solid angle, 4 pi by B. B is the beam area, BW in a E plane. So we can convert this radiation into the degrees as 1 radian. You already know 1 radian is equal to 180 degrees by pi. So if you divide by 180 by 3.14, you will get a 57.295 degrees. So substitute these values in the above in this expression. So you will get 4,125, 41,000, 25,000, 41,257 degrees. Above formula is applicable to the antenna with narrow beam width about 20 degrees with no minor loops in the radiation pattern. E means means this expression is applicable only the uh, radiation occurs in the less than 20 degrees. Means beam width is about the less than the 20 degrees. There will be no minor lobes in the radiation pattern. The beam width of antenna is affected by the shape of the radiation, the pattern, and the wavelength and dimensions. Beam width అన్నది దేని మీద అఫెక్ట్ అవుతుందంటే షేప్ ఆఫ్ ది రేడియేషన్ ప్యాటర్న్, వేవ్లెంత్ అండ్ డైమెన్షన్స్. So let us now discuss about antenna bandwidth. During the operation of the antenna, the characteristic requirements such as antenna gain, side loops, level, and antenna impedance, radiation pattern may change during the operation. Means so when we operating the antenna, some characteristic requirement things are needed. First one is antenna gain, then second one is side loop levels. Okay, how much the radiation can pass from this center to from origin to the certain distance. Okay, next one is antenna impedance, which is called as Z. Okay, the radiation pattern may change. Okay, hence there is no unique definition for the antenna bandwidth. The antenna bandwidth can be simplified in many forms, such as bandwidth over which the gain of the antenna is higher than acceptable value. The bandwidth over which the standing wave. The bandwidth over which the gain of the antenna is higher than acceptable value, or the bandwidth over which the standing wave, the ratio of transmission line feeding antenna is below acceptable value. Bandwidth over FBR in minimum equal to the specified value. So skip these points. The bandwidth of the antenna may defined as the band of frequencies. So note down this. Bandwidth of antenna may defined as f frequency over which antenna maintains required characteristics to the specified values. In general, antenna bandwidth mainly depends on impedance and pattern of the antenna. So you have to remember that antenna bandwidth mainly depends on impedance and pattern of the antenna. Okay. So bandwidth of the antenna depends on the impedance and pattern of the antenna, is inversely proportional to the Q factor of the antenna. Bandwidth, which is equal to difference of these points, W2 minus W1, W0 divided by Q. So bandwidth is different, inversely proportional to the Q factor of the antenna. Wf is the frequency, F2 minus F1 is equal to F0 divided by Q. F0 is the center frequency or designed frequency or resonant frequency. Q factor of antenna is defined as 2 pi times of total energy stored by the antenna divided by the total radiated per cycle. Total energy stored by the antenna by the total means energy radiated by the per cycle. Thus for low antenna, the bandwidth is high. low q value means energy rated per cycle is more, so bandwidth will be more, vice versa. Okay, thank you.